Good morning. I'm back. Thematic information extraction, pattern recognition. And this is mostly about classification. This is the, I guess, the first big question, right? What is it? And so we have different solutions, different algorithms based on either non-parametric or parametric statistics, or also there are some non-metric methods as well. We haven't really done those. And these are not very common. Parametric statistics assume that we know something about the distribution of the pixel values. Non-parametric assumes that we don't know anything about that distribution. So when you do supervised classification, that is parametric because you're sampling, and then you have a sample distribution in your data. And this is just a bit more on these three different categories, different types of classification here. So per pixel, the differentiation here is between, in per pixel classification, we're really talking about hard classifiers like the kinds of classifiers that we've looked at in remote sensing 1, whereas object-oriented classification is more along the lines of unsupervised classification, where you have you have a number of categories or an object that you go into the classification with, and you come out with a number. Your object is achieved. You have a number of classes that are based on the inherent similarities between pixels across the entire image space. Should be very careful, right? Good. That's always a good idea. Be very careful in classification, and you have to be. The way you're being careful is when you write about your classification. You have to be careful with the language that you use, and be very measured in statements that you make about classifications. As you begin to do accuracy testing in the field with classifications, then your language can get stronger, and you can be more maybe less careful, but you can be stronger in your pronouncements about your classification. So in hard classification, it's a very straight linear proposition where you move through the classification. Each pixel is classified into a particular land cover category that you've trained for. In fuzzy classification, you have, and you can think of maximum likelihood as being a kind of a partial fuzzy classification because all pixels are scored on all of the classes, and then the highest score wins. And so how that score is calculated then can be modified slightly as the classification proceeds. You need to make sure you understand the difference between these two things. What we're doing is we're doing land cover classification typically when we do classification, and you should always be careful in the way that you set your classes up. You should take care and set them up in a way that is going to work for your particular classification. And this is a little bit more on that care that you need to take. Again, this is just more about language. Information classes are like residential, whereas spectral classes are the spectral signatures of different kinds of residential that are inherent within a particular image or a particular data set that you may be working with. Classification schemes, there's lots of different ones out there, and the most common come from organizations like the USGS, mostly also Bureau of Land Management, and some other federal organizations have their own classification schemes that they use, U.S. Department of Agriculture. And so it's typical. The most common one, the most common hierarchical scheme is the one that comes from the USGS land cover classification scheme, and it's very useful in most of what we do. And what I do, I just naturally default to it and pretty much start with those categories that that come out of coming out of the USGS classification scheme. So the kinds of classification that we've done in our work in remote sensing is mainly level 3 and level 4, so biome to regional level classification. And you can look through these. These pretty much are resolution or scope scale dependent categories for thinking about different kinds of different classification using different platforms, different sensors, different resolutions. Okay, and again, you have to be careful in collecting your training sites. It's probably best done in the field, although we do a lot. I mean, on-screen selection is it's very common, and that's one where you get most of the savings is by not going to the field as much as you probably should be. But again, we do need to go to the field occasionally. It's difficult to do it in this class because of the 10-week horizon that we work on. So the most common algorithm that we use it's kind of a hybrid between a hard classifier and a fuzzy classifier. Is the maximum likelihood classification algorithm. Classifies each pixel based on the probability of each of the different trained land cover classes, and then it uses the logic that you select to classify each pixel on the maximum likely class that pixel would be a member in. And so again, this is probably where most of the problems arise, possibly in maximum likelihood classification, is in accepting a training sample that is not normally distributed. So you're violating that normality assumption. So when you have a training sample that is bimodal, you probably should take a look at that training sample, and you're really looking at two different things, right? And so you need to split that into two separate training samples, or refine your training sample so that it at least is unimodal. It can be skewed, in either direction. That's not that much of a problem. The bigger problem comes where you have these bimodal training samples, normally with one large mode and then a smaller mode, and you need to take a look at those training samples very carefully when you're doing classification. And when you do that, it's really going to improve your classifications. And again, this is a graphic just showing, and really these spaces out here in between these different classes, this shows the maximum likelihood classification scheme. And again, these spaces are they are classified out here. It's very, very low, the probability, but it gets higher as you look at like the space between say forest and cotton. In there you have kind of a fuzzy boundary between forest and cotton that is defined in a very very fuzzy way, you might say, between those two classes. And then again, this is just another example of that, how these classes actually do overlap, and they all overlap, across the entire image space. The probabilities in some places are extremely low, much lower than 1%. But in fact, this is a really powerful classification scheme, and it's probably certainly been proven to be the most commonly used, certainly, and the strongest supervised classification scheme that we have available to us.